Yeah, so maybe the most important thing I can say is that this is joint work with a lot of people, but this is customary in open source work. I could talk to you about different types of indexes, but I decided to focus on row-ring bitmaps. One of the motivation, of course, is that they're used by Apache Spark, but they're used by a lot of different systems. And so chances are that if you're doing big data in some form, you may have to work with rolling bitmaps, though it's probably under the hood. So there are different types of indexes that do different things. One of the things that we're interested in are set data structures of integers. So it's a very simple problem. We have a set of integers, and we want to quickly check if something is in the set. We want to be able to compute intersection, unions, differences, set similarities, and so forth. This looks kind of abstract, but it's actually all over the place in search engines and just about any database problem you can think of. There are other more advanced operations you might care about because it's not mathematics and we're doing software. We actually want to iterate over the sets, in forward and reverse order. Cool stuff we want to do is be able to jump ahead. For example, you have a large set of integers and you want to, iterate over it, but starting at value 10,000 or later. You want to skip, the early values. You might want to do rank and select, min and max, that kind of things. So for the purpose of my talk here, I'm going to make some assumptions. So your sets have, at least a few integers. They're not too empty. And they span a wide range. And they're mostly immutable. You might be changing them, but you're not changing them all the time, which is a typical assumption in anything that has to do with analytics. So if you look inside your favorite database or search engine and you ask, well, OK, how is it implemented, right? So you'll get different answers. But if you're trying to code things up, you're probably going to use one of the following. You might use a sorted array. For some reason here, I use C++ as an example, even though it's maybe not the most relevant. But so it would be like an std vector in this case, or of course any language as a way to implement an array. Or it could be an hash set, and it could be a bit set, which more and more most programming languages support. Or it could be a compressed bit set, which is the subject here of a talk. We're going to compare these different strategies. And so if you're a programmer, which one should you be using? So a bit set, not everyone, it's fairly common and it's everywhere, but not everyone has actually given a lot of thought about or even knows what a bit set is. So a bit set is a very old idea. But it's very well suited to modern processors. So the idea of a bit set is that you take words, machine words, and then you use them to represent sets in the following way. If, for example, the value 1 is present, then you set the bit at value 1 to 1. If not, you set it at 0. So for example, with a 64-bit word, you can represent every possible set taken from the values from 0 to 64, right? So this takes different names. Some people call them bitmap, bit array, bit set, and so on. So in Java, you have a class just for it. So they're highly efficient, and that's why they're in wide use. So we can look at what happens if we try to. By the way, I'm not using any specific programming language. This is just made up pseudocode that I write. So let's say I want to add a value to bit set. I'm going to do the following. I'm going to try to select the appropriate word and then do a bitwise OR on it. And if I want to check whether a bit set contains a value, I'm going to do a bitwise AND. These operations, they look fairly efficient, but they are also crazily efficient. So basically, setting a bit in a bit set takes about 3 machine instructions on an x64 machine. And because, of course, our processors are multi-scalar, and there's not much in the way of data dependencies and not much in the way of branching and so forth, you can actually set a bit in a bit set once every 1.65 cycles. That's what I measured at home in preparation for this talk. So this is really crazily efficient because, of course, we have billions of CPU cycles. Bit sets are also very powerful in that they enable what we call bit-level parallelism, where when you want to compute, say, the intersection or the union between 2 sets, you're basically doing bitwise AND and bitwise OR operations, which are really, really fast because, and there's no branching, there's nothing. It's really crazily efficient. To give you an idea of how efficient it is, let's say, for example, I want to compute the intersection between 2 bit sets. I estimate that you can do it at about half a cycle on a recent x64 machine, about half a cycle per pair of input words. So if you've got 1,000 of them, that's about 500 cycles to do it. And if you look at the cost of copying 1,000 words, it's about 0.3 cycles per word. So basically, we're very, very close to, at least according to a measurement I took. So roughly, we're very, very close to a mem copy, right? So it's not even twice. So it's crazily efficient. But there's a bit of a problem, is that in some cases, if your data does not fit the right pattern, it can also be crazily inefficient. So if I want to represent a set with a few elements, but one of the value is very large, then I'm going to use like maybe 1,000 bytes per entry, which is really not good. So I'm going to have lots and lots and lots of zeros, lots of words with nothing in them. So this is not good. So for this reason, we use compression. And there are different ways to compress. At the bottom there, we see the memory. Well, here in this table, I'll give you the memory usage for different strategies. So we have the hash sets. In this particular case, I've used for my metrics, I've used the C++ unordered set. You can use an array, or you can use a bit set. In this case, I took a degenerate case where really the bit set is really terrible. Or you can use compression. So you have a compressed bit set. And obviously, the compressed bit set does best because, I chose my example well. The hash set here is doing a bit poorly, memory usage-wise. And this may surprise some of you, okay? But this is actually fairly typical. So hash sets do use quite a bit of memory in general. You can engineer them to be different, but if you just pick up something from your runtime library, that's probably the result you'll get. So the performance. So let's say I've got a bunch of sets, and I want to compute a union between them, right? This is actually a common task, because if you want to do a select a count group by, it may end up actually be implemented under the hood by a union between a bunch of sets, of integers. So here you can see that the hash set does very poorly. The bit set does poorly in this particular example because I chose one where it used a crazy amount of memory. And of course, the compressed bit set does very well. So obviously, what's happening with the bit set is that we're spending a lot of time scanning zeros. It's not too bad to use a lot of memory. Memory can be cheap, but certainly having both high memory usage and poor performance is not great. So really, you should only use like an uncompressed bit set when basically 1 out of 100 bits is in use, right? So this means that your sets should have some density, which basically means that the largest value should not be, it can only be large if you have many values in your integers, in your sets. What may surprise some of you is the fact that I got the worst performance out of the hash set implementation. And this is definitively not always the case. You can engineer hash sets that do very well in this case. But here, for my example, I just picked up, in this case, I used the C++ STL sets, but I would get very comparable results with Java or Scala or any other language. The problem is that in our runtime libraries, the hash sets are designed for basically one value lookup. So they're very, very, very good at that. They're specialized for that. But if you want to compute, say, the union between two hash sets, and you don't there's no API to support this, then you may get terrible performance, because the hash set actually distributes the data more or less randomly in its backing array. And even if for one of, say, if you're doing the union between two pairs of, between a pair of hash sets, even if one of them you're reading sequentially into backing array, in the other one you may actually end up being jumping around all over the place, and you're hitting a new cache line each time, and that's not good. And if you've got lots of data, this translates into cache misses and possibly expensive ones, and that's really terrible. Here I wanted to give an example of that where hash sets can degenerate. So Apple has this new language that's fairly popular, but interestingly, I don't even know whether it's possible to query Spark from Swift. That'd be interesting. I didn't check, but anyhow, I wanted to use it as an example of how runtime libraries can lead to problems. So here's a very simple example of code where you just build a set, and then you take the very set that you just created, and that's going to run very fast. You're going to insert your data into set very fast. And then you just take it and you dump it into another set. This looks, totally safe and totally good and so on, but this will actually run rather terribly. You'll have actually quadratic effects at play. And you can get the same problem with Java if you use, for example, the fast-util library or some of the other fast data structure libraries. You may actually get this problem too. And this looks a lot like a union, as I was showing before. So this is sort of an example where hash sets can let you down. Arrays are, so what about arrays? That's another way to implement sets of integers. And they're fairly good. Of course, you can compress sets. So there was a talk previously about Parquet, and Parquet has techniques to compress arrays. But I decided not to talk about compressed arrays. But just a standard array, of course, can be not very economical, but it's generally relatively safe, all things said. But one of the big problems it does is searching in an array can be sometimes unacceptably slow, because you're going to use a binary search, and a binary search over a lot of data can be a little bit bad, because you've got all of these branches, and of course branches are not great, but what is worse is that then when the processor cannot predict the right branch, then it cannot prefetch the data, and so you get these expensive branch misses. So, and again, these numbers, you can check them out online. I gave the URL earlier, so you can run a program that tests these things. And so you have an example here where, for example, the arrays get totally degenerate value lookups. And we really want indexes to have good all-around performance. So far I've not discussed how you compressed bit sets. So there are different techniques. One technique that's probably the most popular is run length encoding. So run length encoding is very, very simple. The idea is that you expect your bit sets to be made of sequences, of continuous sequences of zeros and ones. And basically, if you've got a bunch of zeros, instead of storing them, you can say, well, I've got 1,000 zeros. And of course, you can store this information using only a few bytes. Right? You don't need to actually write out the zero fully. So you would actually use a format that's optimized for bit sets. So there are different ones. So Oracle has one, BBC. There's a system called FastBit. I think that the author of FastBit was giving a talk earlier. There's also EWA, which you're using. If maybe you know about this site that's called GitHub. So they use Git, and so if you use it, well, then it's you should know that it's using compressed bit sets using run length encoding to accelerate its queries. So I give the hyperlink here about the technical blog post that describes how it was done and why it was done to accelerate the queries. Apache Hive also uses those, and so forth. And it's all fine. It works really well when it works, but there are some problems with it. All of these formats, for example, have a relatively poor worst case. For example, if you want to query a value, sometimes the only thing possible is to actually start from the beginning and scan the entire data until you get to the point where you want to You want to check whether where the value you're looking for would be. And so that's, bad complexity. It's ON complexity. And actually, it does deliver really poor performance in these cases. And there are all sort of cases where it's kind of bad. For example, we would want a compressed bit set to have the same performance in the worst case as a bit set. When the bit set is really the most appropriate, it's basically not very compressible. We would want the performance to be roughly the same as a bit set. We don't want compression to come at too much of a performance cost, but these formats sometimes they fail to deliver. So a few years ago, we went back to a model that had been put forward by Patrick O'Neill and also by the folks from BitMagic, and we decided to revisit and try to improve an old model where basically, and that's basically roaring, what we do is we take the space of possible integers and we look at we divide it into 16-bit chunks. So the first chunk would be the numbers from 0 to 65,000, and then the next 65,000s would be another chunk, and so on. So we divide the space into these fairly large chunks, and inside each chunk, we use one of three possible formats. So either it's a sorted array, it's a sorted array of 16-bit integers, or we use a bit set, or we use a sequence of sorted runs, right? So we use one of three possible formats. So this means that the same data structure may, inside it, contain different we call them containers, different containers having different types, right? And this design works in the following characteristics. So one of them is that all these containers, they fit in 8 kilobytes. So they fit in your fast CPU cache. So that's really important in some cases. When we built, and that's really an engineering challenge, when we build the bitmaps, we have to sort of optimize it so that it picks the right container type so that you have good performance and good speed. And sometimes we get help from the programmer who can call run optimize to actually compact things further. And it's all optimized for very, very high speed. So here I could give you like lots of results, but I picked one example here. And again, all these tests are available online. So it's an example where I compare different formats. So on top, the first format is just an uncompressed bit set. At the bottom, I've got roaring. And these are the number of CPU cycles, so it's time to compute union, the union between bit sets, between sets. And as you can see, all the running length encoded format they're several times worse than the compressed bit sets in this case, whereas rolling is just as fast, right? And that's really the objective we seek. We want to save memory, lots of memory, but we also want to achieve the best all-around performance we can. So I'll use the second. So I'm giving a second talk, deep dive, where I'm going to explain a little bit more how we can engineer it. But I'm just going to give you the gist of it, what makes it possible. So one really nice feature of modern processors And this is the processors that Intel gives us, or basically all of them, ARM and so on. All the modern processors have really fast ways to compute, to count the number of ones that you find in a word. And this turns out to be critical because this allows us to count, to maintain the number of bits set to 1 we have in our bit set containers. And that's important because we want to know the cardinality so that we can revert back to an array sometimes, or do all sort of, or pick the right heuristic. And it's really powerful that we have these really fast instructions. 20 years ago, it would have been much more painful to do because the processors did not have these instructions. So it makes it, for a different reason, makes it fairly inexpensive to keep track of the values, the number of values, and so on. And another thing, another nice feature we have is that we found that in practice, it's a heuristic, but in practice, having the choice between an array and run, or a collection of run, and a bit set, it covers a lot of cases. So it makes the performance pretty good in practice for a lot of cases. So yeah, so it's available in different languages: Java, Go, C, C++. Obviously, Spark uses the Java version. We have a documented interpretable serialized format, so you can save your data in Java, load it in Go, and so forth. And we have papers and so forth. And it's all on GitHub and free.
All right, thank you, Daniel. If you have questions, we have 2 microphones over there. Now, I have a question, actually. So is this, how much of the code is written with low-level assembly, and how much can be written in higher-level C++ or Java? I mean, because you talk a lot about the primitives that you need to use.
Right. Well, so we have distinct versions. So we have, obviously, the Java version does not have any assembly. The C version does have a lot of low-level optimization, including some hand-tuned assembly, which I'm going to cover in the next talk. Yeah.
I think you said that between the projects, there's checks for compatibility between language implementations. Is that right? How about for compatibility of serialized form between releases?
Yeah, the format is static, so it's not changing. And if it were to change, we're committed to actually supporting the existing format, but we're not planning on changing it. And also, the way it works, for example, there's a system called Druid, and they actually memory map the format, so it's designed so that you can actually access the data without first loading it up in memory. So it has some nice features that you can, so you can jump ahead to the right container and directly from the format. So yeah, the format is static. It's not, say, Java serialized or Scala serialized or pickled or something. It's something that it's really handwritten.
Thank you.
You mentioned Scala serialization. I have an app that I'm thinking of that basically it's a Spark app in Scala that I'd like to throw values into these roaring bitmaps. I'm just curious if you have any suggestions. Typically when I do that, something with Java, I always get those serialization errors. So is there any implementations you would suggest to start with to try these out?
Well, we can talk after if you want, but yeah, we can talk after if you want.
Any other question? All right. So thanks, Daniel, and I'm pretty looking forward for the second half of the talk in a few minutes.
Thank you.